The third and final observation that was made was that the maximum kinetic energy of these emitted electrons over here increased together with the frequency of this radiation over here. Now, this, of course, is a direct contradiction to what wave theory predicts. Again, wave theory says that energy and frequency has no relationship, but here we are showing that if the frequency of these photons went up, the electrons would then be emitted with higher kinetic energy. So what we're going to do now, we're going to investigate how Einstein figured that out. And so, very interesting, he switched the polarities of this cell over here such that now I would get a positive potential here and a relatively negative potential there. And so the key difference between this and the original setup is that now the electrons, instead of being pulled across, would now have to fight a field that is trying to push it back to the zinc. And so, let us imagine what happens. Remember that the electrons are all being emitted with a certain amount of kinetic energy. And so, given any kind of resistive potential, some electrons with not so much energy would go halfway and turn back. But some electrons who are strong enough with enough Ke may still be able to reach the opposing plate. And so Einstein started to collect this data using this voltmeter and this ammeter. He plotted a graph of the potential difference V, potential difference is here, V, and the current detected in the milliammeter. Okay, and of course, he realized that when the potential was positive, everything was fine. Okay, but during the negative potential, he realized that the more negative he made the potential difference, the less the current became, which is understandable because less electrons can reach the plate. But what is interesting is that if I focus on this value over here, when the current becomes zero for the first time, what would this correspond to? So this would correspond to that moment where that one electron with the maximum Ke just did not make it across. And so at this special point where the current goes zero for the first time, we call this the stopping potential. This is the negative potential difference that you apply across the plates so that the current goes to zero for the first time. And it is at this point, okay, for the electron with Ke max that it loses all of its kinetic energy and it's converted into electric potential energy. And so remember, now I can figure out Ke max, and this is simply equal to Q delta V, which is EVS. And so this is how Albert Einstein calculated the kinetic energy. And so upon repeated experiment, when he plotted Ke max against the frequency of radiation, he found, of course, that as the frequency went up, the Ke max went up. This, of course, over here is the threshold frequency, okay, below which there is no photo emission, and so there is no Ke max to talk about. And let's pull it all together. Recall Einstein's photoelectric equation, like this. If I rearrange this, I will get Ke max equals to HF minus phi. And so the gradient of this line is indeed h, Planck's constant. And if I extrapolate this line, the y-intercept will be minus phi.